Okay, this video is all to do with the atomic structure, the physics topic. Okay, question number 1. In terms of subatomic particles, what are the following? An atom. So when we're talking about subatomic particles, we're talking about protons, neutrons and electrons. So in an atom, it is the same number of protons and electrons. Okay? An ion has an unequal number of protons and electrons. So an ion means a charged particle. So if you've got an ion, if it's got more electrons in it, then it's going to be negatively charged. If it's got more protons, it's going to be positively charged. The mass number is the sum of the protons and neutrons. The atomic number is the number of protons. Okay? It's often the number of electrons as well. Question number 2. Complete the table for the subatomic particles. Neutron, charge, no charge. Proton, positive, electron, negative. The relative sizes, right? A neutron, size 1, proton, size 1. Now, there's kind of no units to it, but basically what it's saying there is saying that they're both the same size. Now, an electron, you could have size 0, you could have tiny, or you could have the word negligible, which basically means there's very, very little of it. Where are they found? Neutrons are found in, what am I doing here? Nucleus. Protons are also found in the nucleus. Electrons are found in the shells. What piece of equipment is used to detect radiation? This is called a Geiger-Müller tube. Okay, or sometimes it's called a Geiger counter, and it's one of those machines that kind of goes like a clicking noise when it detects radiation. What is background radiation? Background radiation is the radiation all around us. So for example, I'm sitting in this room here and I'm getting bombarded by radiation, all right, but it's just very, very low levels of it. Here, name 2 natural sources and 2, I think that should be man-made sources of background radiation. So 2 natural sources could be rocks. If you go to places in Scotland, right, where they've got granite, there's large amounts of background radiation. And you've also got cosmic rays, right? So cosmic rays coming from outer space, coming from the sun. 2 man-made ones is from nuclear weapons testing. Okay, so wherever they've been tested, there's going to be considerably more background radiation. And you could also have nuclear accidents like Chernobyl, right? They're possible ones of man-made background radiation. Question number 6, right? This kind of goes back to sort of information about question number 1. What is an isotope? An isotope is the same element with a different number of neutrons. So for example, you could have lithium 7,3, and you could also have a lithium 8,3. Now whether they exist or not, it's not the point. The point is the fact that what you've got on there is you've got different numbers at the top, but the protons stay the same. Right, number 7. What are Rutherford's 3 observations? All right, now this repeats itself loads. It's even repeated on this test. All right, so number 1 is the alpha, so this is all about the alpha particles, okay, which are then 2+ charge, so they're positively charged alpha particles. Most of them go straight through. And what that means is the vast majority of the atom is empty space. Question number 2. Some of them are deflected. Okay, so basically it's talking about changing direction. That means there is a positive nucleus, right? Because as the positive alpha goes near the positive nucleus, they repel each other, and so the actual alpha particle changes direction. Bounce back, that is because there is a solid nucleus, right? So the alpha particle hits the solid nucleus and literally bounces back from where it came. Question number 8, radioactive decay. It is where an unstable nucleus over time randomly emits ionizing radiation. Okay, so the key to that is the fact that the nucleus is unstable, and then every now and again, right, you don't know when it's going to happen, it will then randomly break down and emit ionizing radiation. Question number 9, all right, particle, alpha, beta, gamma. Symbols, alpha, I'm never very good at drawing these. Beta is kind of like a bee with a tail going out the bottom of it. And gamma, right, looks like a fish standing on its head. What is it? Alpha is 2 protons and 2 neutrons. And often what it's called a helium nucleus. Didn't fit that in very well. Beta is a fast moving electron. And gamma is an electromagnetic wave. So it's pretty much like a wave of energy, right? There's kind of no physical substance to it, it's just like a wave of energy. Alpha's charge +2, beta's charge -1, gamma's charge 0. There is no charge. Range in air, right? It just kind of follows a pattern now. So the range in air for alpha is a few centimetres. Range in air, a few metres. And then range in air for gamma, right, you could write down many, many thousands of kilometres, all right, or you could even write infinite, right, it could just keep going. Penetration and what stops them, right? So penetration basically means how far it can travel into something. So if you know what stops them, it gives you an idea about how far it can penetrate. Alpha is stopped by paper. It's also stopped by a few centimetres of air. Beta is stopped by thin, I can't spell today, thin aluminium. Okay, sort of a bit like sort of thickish tin foil really. And gamma is stopped by thick lead or thick concrete. Ionization power, ionizing power. Ionization is the damage that can be caused to cells. So the ionization of alpha is very high. It causes damage very easily. Ionization of beta is medium, it's in between, and the ionization of gamma is very low. Okay, now question number 10, right? Again, it's been on another video already, right? But what we've just got to do is we've just got to make sure that we're remembering it each time. So Democritus came up with the word atomos, right? Which basically means cannot be cut. John Dalton, he came up with the principle that they were a solid sphere. Okay, it's kind of what we draw these days, kind of when we're actually drawing molecules and things like that, but obviously it's not correct. J.J. Thomson came up with plum pudding. What that is, it is a sphere, right? And in it, what it's got negative charges. Okay, so those negative charges are then the electrons that are embedded in, and kind of like the doughy bit are positive. So his plum pudding is like a positive doughy pudding with negatively charged electrodes within it. Some people call it like a bit like a chocolate chip cookie, where the cookie bit is the positive and then chocolate is the negative bit. Rutherford, right, this is the kind of the one that's tested the most, right? So straight through, we've already done this in this test itself. That means empty space. Deflected, okay, so that means change direction. That means a positive nucleus. And the other one, or the third one, is he noticed that some of the alpha particles, I'm just going to write down alpha there again, 2+, right, it's a helium nucleus. Bounce back is a solid nucleus. Bohr, right, this guy here, what he then did is he came up with a principle that electrons are in shells. And finally, James Chadwick, he came up with a principle of neutrons because he realised there was something in the middle of the atom that weighed something but nobody discovered. Number 11, complete the following equations. Right, now this is just like straightforward maths. The top numbers have got to add up. So basically 238, take away 4, makes 234. 92 and 2, those numbers need to add up, is 90. Right? But the most important about this, if ever you're given an equation like that and they talk about alpha, you have to remember that. Right? 4,2He. The next one is, we've then got this here. This, so that is alpha radiation. This is then beta radiation. And that is then a symbol for beta radiation. The numbers then need to add up again. So 14, take away 0 is 14. 6 and minus 1, that has to be 7. Right? Sometimes people will put 5 because it kind of makes sense, but it isn't. It's 7. The last one, gamma. Gamma basically has nothing at all, so it stays at 99 and 43. 2 words. Question number 12, what is contamination? It is the unwanted presence of radioactive atoms. Okay, it's basically something's got something that shouldn't be there. All right, so you could have a piece of meat, right, that is contaminated because it's got the unwanted presence of something. But from a radiation or science point of view, right, it's the unwanted presence of radioactive atoms. Irradiation is where something is exposed to a radioactive source. Okay, so I could put a radioactive source on the desk and then people are then getting exposed to it. And that is irradiation. Question number 13. Right, so what we've done is we've got a graph. Right, first thing you do with a graph is you always look at what the units are. So disintegration rate, decays per minute, time in days. Right, and what you just got to do is you just then got to use the graph to work out answers. Half-life number 1. Up here, it's 16,000. Down here, half of it is 18. So the half-life is the amount of time it takes for half of it to disappear. Then what you do, not like me, right, you then get a ruler out and you go across to there, and then you go down. So the first half-life is 8 days. Okay, don't miss off the days. Second half-life is, so I've got 8,000, I go down to 4,000, and then what I do is using my lovely straight ruler, I go across to there, and I go down there. But I don't write 16 days, because that's not the half-life. What I do then is I write down 8 days again. Question number 14, what is a half-life? It is the time taken to lose half of its initial radioactivity. Okay, so a half-life could be milliseconds, or a half-life could be tens of thousands of years. It all depends on the substance. Question number 15. Now there's quite a lot of keywords in this one, right? And I'll say it a million times, right? What you've got to do is you've got to use the keywords. If you don't use the keywords, you don't get the marks. All right? So, question number 1. The rate at which an unstable nucleus decays is its activity. A positively charged particle, because there's 2 protons and 2 neutrons, and there's a helium nucleus, is an alpha particle. Radiation that is found in small quantities all around us. Okay, that tells me immediately what it was. It's come from man-made sources, etc., is background radiation. The unit of radioactive activity, right, is a funny sounding word. It is a becquerel. A high-speed electron that a nucleus emits when a neutron converts into a proton, right? So we're talking about radiation, right? High-speed electron is a beta particle. Number 7. A model of the atom suggests that electrons orbit the nucleus at set distances, shells, right? Think about our diagram from before. It is the Bohr model. The number of decays that a detector measures per second is the count rate. Question number 9. A negatively charged constituent of the atom that are found in different energy levels around the nucleus. The electron. Okay, you just got to look at it and you just got to pick out the most important facts and it tells you all the answers. Electromagnetic radiation emitted from the nucleus. Gamma ray. A detector that measures the count rate of a radioactive substance. Okay, that's our is a, I'm just going to write down Geiger-Müller tube. Okay, I'm being lazy there, right, because I can't fit it in particularly very well. Number 13, the time it takes for the number of unstable nuclei of an isotope for the sample to half. Okay, well, do you know what that is? Half-life. Number 14, atoms with a resultant charge due to the loss or gain of electrons. So if it loses electrons, it's going to become positive. If it gains electrons, it becomes negative. All right? So they then form ions. Number 15, the process of an object being exposed to nuclear radiation, the object doesn't become radioactive, is irradiation. Okay, that is then when they're exposed. Atoms with the same number of protons but different number of neutrons. Isotope. Number 19. A neutrally charged constituent of the nucleus. Neutron. Number 21. An old model of the atom that represented the atom as a ball of positive charge and a negative charge distributed through it. Plum pudding model. A positively charged constituent of the nucleus, proton. Number 24, the unwanted presence of radioactive atoms is contamination. 25, the random process involving unstable nuclei emitting radiation to become more stable is radioactive decay. And the final one, the unit used for radiation dosage is sievert. So that is a measure of how much radiation you've actually got.